welcome to today's session on Python and machine learning. Hope you're having a very nice time attending all of these lectures by the faculty here. Today will be a bit more hands-on, so I will be giving a lecture of sorts, but I'm going to give you a lot of resources, so you can take this back home and work out stuff yourself. Initially, this was intended to be a very interactive kind of tutorial, but due to time constraints, we will not be very interactive. But I will give you a lot of take-home assignments. You just need to run some code, and you don't need to install anything. Just run it all online. So with that backdrop, let us get started. And I will share my screen now. And there you go. Yeah. So I think you can all see my screen. So yes, so this session will be for 2 days, or rather, this is split over 2 days. The first day, that is today, for the next hour, we'll be looking at what Python is and some measures of working with Python and working with data and stuff like that. And tomorrow, we'll be looking at some machine learning aspects. I'm not very sure what the level of understanding in both Python and machine learning is for the audience here. So I'll try to keep it as simple as possible, but it will get a bit complicated as things go on. But here's the thing: the internet takeaway is not for you to become an overnight expert in ML or Python or anything. Basically, we want to open data and visualize them as astronomers or as aspiring astronomers. This is what we want to get started with doing. And once we have data, we need to perform operations on these data. And once we can perform operations and all, we can ask proper science questions. And possibly there are some places where you can use machine learning to enhance the science that you do. And for using, if you want to use ML, you need to have a basic understanding of what these various techniques are. And there are various steps involved in a typical machine learning project, for example, that you need to have data processing, the choice of algorithm, etc. So you don't just start by writing the algorithm. You start by reading papers, reading tutorials on how things are done. And then you're able to critique whether a certain choice of data processing was correct or not in these papers. And then you go and phrase the correct problem to use the ML algorithm for your work. So you have some science question, you need to let's say automate some Python or something. So that's how you phrase your problem. And finally, once you have a basic understanding of the effectiveness of various techniques, then you apply them to your various tasks. So that's the way you form ML. So the menu for today is what is Python and where do we code, some data types we use it, some packages, some simple examples. What does astro data look like? Because we don't want to so Python is a very massive environment. You can get lost in the forest, but we don't want to get lost in the forest. We would rather want to look at some astro-oriented aspects. And finally, we have some exercises. So, what is Python? Python is what is called an interpreted language. It's a very high-level language, which is the primary emphasis of Python is on code readability and use of indentation for figuring out what parts of the code belong to a given subcode or not. So the key word is interpreted language, and code readability is the basic aim for writing Python in the first place. And of course, indentation is how you people generally figure out whether something's written in Python or not. So you have indentations by and large is Python. So these are the three keywords. And why Python? So you can ask me before even I explain all of these things. So we have umpteen languages, right? We have C, C++, Fortran, I don't know, Julia, R, and whatnot. So why Python? So the biggest advantage offered by Python is that it's open source, which means that you don't need to buy anything. I mean, there are obviously packages where you may need to buy something, but by and large, you don't need to buy anything. It's all free. It's all available everywhere. So just download whatever you want, use it, and try to make your thing be available for free for the community to use. And also, since it's open source and since anybody starts to use Python, the support community is very strong. You can ask a question on Stack Overflow or any of the Python forums, and people will get back to you with very good answers. So this is how the whole setup evolves and has been evolving over time. A quite supportive community, along with a lot of open source code, helps us in not getting lost, or even spending tons of rupees, tens of thousands of rupees on getting some code out. So, in other words, so if you have a task, so let us say you have a task that says print my world or hello world, whatever you want to. So you or we as humans read in some language, English, Hindi, or any language. But the computer doesn't understand this language at all. The computer just understands zeros and ones, right? It just understands the binary language. So it's just some voltages present or not. So that's what it understands. So whenever you give any input to a computer, this input needs to be decoded into a language which the computer understands. And there are various ways of doing this interpretation. So the first way of, or general way of doing it is, if you have a C code, if you know if you know a bit of C language, there is something called compiling the code. You compile the code and then you run the. So what the compile does is it reads to the whole code that you have and generates a string of zeros and ones. And this 0 and 1 is given to the computer, which it then reads and does whatever task it is asked to do. So this is called a compiled language. You take the whole thing together and compile it all together. That's a compiled language. But then what can also happen is that you can take bits and pieces of this code and just interpret them into the binary code. So parts of it come out. So the first line comes separately, second line comes separately, so on and so forth. So the computer takes in dynamically, almost in real time, the interpretation and execute and generates the output for whatever input you are giving. So this is called an interpreted language. The difference, there's only a very simple difference. Is the translation from human to machine done all at the same time or one by one? So you can ask me, even this figure here, and this is taken from some source here, you can see that the computer is wondering why is it giving me one line by line. So the thing is, it's not bad. So the point is, since you are doing it line by line, you know what is happening on each line. So if you use a C compiler, for example, you might have an error somewhere, but the compiler might throw an error somewhere totally else. So you need to keep navigating somewhere into the whole code base and then figure out where your error is. But if you can compile stuff, block by block, then you're essentially debugging your code in various parts, and this makes your life very, very easy. And then you can execute blocks of code together. So we'll see what happens when you do this. So you don't need to run all of the code at the same time. You can just let some code run and then keep changing some other parts of the code, so you don't lose any data or so. So this makes it, primarily it makes it very easy to debug and easy to prototype. So prototype in the sense, if you're developing a new code, let's say, so you don't, let's say you're writing a pipeline for some processing some master data. You don't need to be loading the data each and every time to process this pipeline. So you just need to load the data once, and then what your intended problem is to write the pipeline, not to load the data every time. And if your data is like some 5 GB or something, you will not be loading the data every time. Right? You load it once, and then you try to debug whatever pipeline you have. And Python makes it easy because you have one region where you just load the data, and you have the other region where you just prototype the data, prototype your pipeline, and you keep prototyping it, you keep debugging all the errors off, and then finally you have a nice pipeline which works, and then you run the whole code together. So this makes it very easy to write code, and it's also very easy to teach. So the way I teach you, I find it much more easier to teach in Python than, let's say, in C, wherein you have to write the whole code and then compile it and then run it and so on and so forth. So another technical advantage offered by Python, for example, is that compatibility issues are sort of reduced. What this means is you need to have a specific compiler, for example, in C or Fortran to compile the whole code. In Python, since it's line by line, it's on the fly essentially. You don't have such strong, stringent constraints on the compiler properties. You still obviously have some prerequisites. It's not going away, but then it is not as strong as, so you have GCC 5.1 or something. It's not going to work on 5.2. Those things generally don't happen. You can resolve them very easily in Python. So an example of a Python code here. So let's see. This is a C code on the left hand side here. So what you basically have is you have to import some package, and you have a main function which is executed, and then so this is C++. It's not even C. It's C++. So you say C out hello, and then you have to compile this code, and then you run this code, and then you get hello world on your screen. That's what you do. In contrast, in Python, all you do is this: so print hello world. That's it. You're not doing anything else. There's no IO stream. There's no void main. Nothing. Just a print function. So you can see how verbose C++ looks when compared to Python when performing this action. Of course, this is not to say that Python is super great and all. C++ or C or Fortran are very fast because they're compiled. And there are other technical. So if you want to write simulation codes and so on and so forth, you use C. If you want to build up on some simulation codes, you use Python. So that's how things work. So how do we write our code? Right now we'll be using something called Jupyter Notebook and Google Collab. So Google Collab is this online code editor, if you want to think about it like that, which gives you access to free compute, and you can easily write codes. Give me a minute. Yeah, you can easily write codes, and you don't need to install anything on your computer. You can just use it directly. So what we'll do is I'll send you a link on the chat below, and within that you can find all of the necessary materials required for this lecture. And we'll just go to the Jupyter Collab and look at what the various exercises are. So let's move on to Jupyter, and for that I'll stop this presentation. Let me share the link. So this is the link for the to my GitHub repo, which I shall be sharing with you on chat. So for those of you who would like to follow this tutorial, just go to this link and click on this python underscore intro.ipynb. Just click on this and you'll get something. Let it come. Yeah, so that's what you get. So this is the notebook that we'll be following. So what we'll do is you click on this open in Collab button and you get a new tab like that. So you get a new tab like that. And then what you do is you just say connect to kernel on right side. Just connecting to kernel. It will take some time. It's initializing. Let's see. It's connected. So what you do is you just say shift and enter. Shift and enter at the same time. And then it will throw up some dialog box, but you run anyway. And that's it. So that's how you run Collab. It's as simple as that. So this is what we'll be using for today's and tomorrow's work. So I'll just close this one because I have some data and I have some stuff open up. So let's see. The first couple of things we need to understand when we do Python is we need to know what these various data types are. So there are a lot of different kinds of data types like integer, floating point numbers, so on and so forth. So we need to know what these are. And Python doesn't handle these data types in the way C or C++ handles. So it handles in a very different manner. And we need to know what this is, and we need to also know what the various packages are. So once you know the data types are, once you know what is object-oriented program, which will go in a couple of minutes, you'll also need to know how to use various packages and get the data out. So let's do this. So let's look at a typical code that we have here. Let's go block by block. So if you are following this tutorial along with me, then as we proceed, you can keep proceeding forward. So here, what we do is we just take a variable named x and assign a value 5 to this variable. And you can just do a print x, which is basically printing the value that is present in x, and then also say print type of x. So type of x corresponds to the data type, which is data type of the variable x, and that will be printed. So let me just not do this and just print this here. So if I do a shift enter, this is what we get. Obviously, x, the value of x is 5, and it's an integer, right? What Python offers us, since it is interpreted line by line, I don't need to, fix this variable x as 5 as a data type integer just in one place. I can rewrite the data type of x as something else. So I can write it as IUCAA. So the double quotes here means a string. So this means a string. And if I just run this cell, it says the class is str. It's a string. So you can see that the variable x was given a value of 5. It took a value of 5 and it said the data, it's an integer of type 5. I gave the variable x a value of IUCAA as a string, and it gave me a value of IUCAA with a class with a data type as string. So again, so this is just this is the same thing. If you between across various strings, the data is similar. So if I define x as IUCAA somewhere and don't change that x value anywhere else, it means that it is going to hold the value for the rest of the loop. That's the way it generally works. So yeah, so this is pretty cool about about Python. So you don't need to bother with defining the variable empty variable, and then you can't change the data type of variables, so on and so forth. So this is about integers and strings. Now what Python also offers is something called a list. A list is basically just a collection of stuff. So the list here is this. If I have a if I redefine x now again as stars, galaxies, and quasars, and if I print this cell, x basically contains this thing. This is a set of bunch of strings, and it's called a list. So what we can also do is we don't need to. It need not be just strings. It can also be some number. Like let's say I don't know 41 for whatever reason, 100. So a list is basically a collection of stuff. It can be a collection of strings and integers, maybe floats. So 1.1 maybe for all we know. This is a floating point number. So a list can contain whatever it is that you want. It can contain any data type you want. It's just a collection of objects. So what makes it versatile is that you can keep adding stuff to a list and keep populating it. And if you want to add, let's say, a new number to a list, to the existing list, you just say list.append of whatever the new object is. And then if you just print x, what you get is the new list with the old variables, the old objects present, and the new number 42 being added to the list. So a list is a very versatile placeholder, if you want to think about it, which is basically just a collection of objects. Okay. So this is not this is not ordered in the sense that you don't have mapping from some A to B. It's just a bunch of collection of objects. If you want a special set of mapping from A to B, you have something called a dictionary. So for example, again here we have a mass of 10 to the 2 times 10 to the 30, a radius of 6.9 E9, I think it's in centimeters, and this is a G2 type G2V type with a surface temperature of around 6000 Kelvin. So if you know what this object is, just put in the chat what this object is. What are we talking about? So what if you define a dictionary like this? It says that the type of X is dictionary, where the mass is 10 to the 30, the radius is so much, the type is something, and the surface temperature is something. The surface temperature is in Kelvin for all this. So this is basically the let's see, has somebody put in chat? Please increase font. Okay. So seems like you're having some problems with font. Is this font better? Can you please confirm in the chat this font is better? Just give me a moment. Maybe we'll see the chat. The font is better now. Yes. Okay, great. So this is typically your these are the typical characteristics of the sun actually. And all it says is if you have a mass of something, a radius of something, a type of something, and surface temperature of something. So that's the kind of mapping. So in a dictionary, these values here, the first values here are called keys, and the other values are called items. So for each key, you will have a corresponding item. And this item can be a number. So this key can be a number or a string or whatever. Even the item can be something, whatever you want. And you can also always add a new element to this dictionary, which is called, for example, here I'm saying luminosity, where x of luminosity is one solar luminosity. If I just print x, this is what you get. Luminosity is so much, mass is so much, radius is so much, so on and so forth. This is what you get. So this is the way you have various data types that are going about in Python. So you have your typical data types like int, float, char, string, so on and so forth. And you also have new object kind of, or say aggregators, if you want to think about this, called lists and dictionaries. Now you look at various functions. So you just don't want to define some stuff and let it be there. Right? You also want to manipulate them. So if you want to manipulate them, you need to define functions because sometimes you keep performing these manipulations multiple times. So for example, if your x is 7, y is 9, and z is some weird function I've written here for whatever reason, and you print z. So this is the value of z that you have here. Now what? Hello? Hello? Is there some issue? Hello, yes, somebody is unmuted. Yeah. If you have a question, just feel free to stop me and we can have a discussion. It's perfectly fine here. Because in the end, it's not about finishing this whole syllabus. It's rather about you taking away something from this. So yeah. So back to our functions. So this is if you want to automate this process. Let's say you do this operation, this z equal to something multiple times. Like let's say you have to do it some 1,000 times. You typically define a function. And a function is basically defined like this. You say def, some function name, and v1, v2 are the inputs that this function takes. And then you have this colon here. And once you have this colon here, you need to give the proper indentation. So I told you about the indentation, right? This is the proper indentation you give. And with the proper indentation, you define whatever stuff happens in your function. And then you return a value which the function computes and gives the result. So for example, if I just run this cell, and if I do fun of x comma y, I get the same value as what I got here initially. Okay. So this is typically how you define functions. And so you have a bunch of data types, you have a collection of objects, and then you have functions. So these functions can take these data types or these variables, perform some operations and manipulate them, and return values, whatever stuff that you want to do. If you want to have a function which returns square root of a number, sure, you can do that. Or if you want to find the roots of a polynomial, for example, you can do that. And in a more complicated manner, if you want to fit a Gaussian to a spectral line, then sure, you can do that also. That's how you define a function. So these are some basic aspects of Python. Now let's go into a bit more detail. So let us take a step back and go in a bit more detail actually. Let us just define x to be an integer 2. Okay. And let's just say help of x. Help is a special function. So it's literally crying for help. It tells you everything that is to know what is variable x. So if I do help of x, you can see that it's very, very verbose, right? It says class int of object. It doesn't say x is an integer. It says x is a class of integer. And then it has given a lot of stuff. It says some add function, some and function, something. So you can see that these are all functions, right? You have a function name, some input, and then some output here. And sometimes output. So return self star val and some stuff like that. You don't need to know what these functions do. But it seems to be extremely verbose. So you would expect that an integer would just be a number. It would not be something really complicated. But it doesn't seem to be the case in Python. But actually, this is what helps Python to be so versatile. So every variable every variable in Python is an object. You can take an integer, a floating point number, or a string, or whatever you want. Everything comes as a class object. So what is a class object? For every class object will have is basically a collection of functions and variables. So you can think of it like that. So think of it like a house or a library. So every house has its own special properties, and which is only specific to that house. And then there could be multiple such houses, right? So if you think of integer to be like a house, and then you can have multiple such houses. So you can have multiple kinds of integers. But the essential characteristics in the house, that you have a kitchen, you have a room at least, a bathroom, for example. These things are common across most houses. So the same way, if you take a class object, the way you define it is you say class, which tells you that you're defining a class object, and number. So class number is the name of the class object. So like int, float, string, number is a data type. So or you can think of it like a data type. So number is a class object, is the name of the class, is the name of the class variable, and again you have a colon there. And then the first function that you generally define is called the init function. Underscore underscore init underscore underscore. So this init function initializes the class, and any variables that the class holds is being initialized in this init function. So what you do is you have something called self, which means it is telling myself. It's about me, or it's about the number class itself, and some value. And this value will be something you will be passing to it separately. You will be giving it separately. So when you said x is equal to 2, self corresponds to the x as an integer itself, and 2 corresponds to the value that you're giving it to the integer. Okay. So when you do an init function, what you're doing inside is you say some that value equal to value, or you say the value inside x is equal to the value is equal to 2 or whatever the value is. And then you can define a function called add, for example. What I'm doing here is I'm just writing a very short hand for a number for an integer class. So I can define add function and say return a number where the value of the number is self.value, that is the value that I have defined for myself, and the value that I have gotten from some other number. And then I can say define a string and say what the self.value. So define underscore string will give you the output is called when you do a print of that value. So this seems very complicated, but let's look at what the code actually does. So you say a equal to number of 2. So what this does is a has something called is a has a value, and that value is equal to 2. Similarly, b has a value, that value is equal to 3. So let's just run this cell. Let's just run this cell also, and let's say a dot value. So a dot value is 2. Okay. Similarly, b dot value. It's taking some time. B dot value is 3. And now what we do is we can do a plus b. We can do a plus b. See, a plus b is a class value. It's a class. It's a class of type number. So you need to define it somewhere. So you say a plus b equal to c, which is another variable. So which is again a class now. And when you say print c, you should get 5. So this is how the manipulation works. So when I said plus here, this plus was replaced by this add function of a. So I can as well do a dot underscore add underscore of b and say print. This is again giving you 5. So the equivalent of this command is basically a plus b. So wherever the code encounters something like 1 plus 1 or 3 plus 1, what it basically does is it takes the add function of 3 and then adds the value present in this variable called 1, and gives you the final output. So this is how the addition operation works. This is how the subtraction also works, or any operation works. So all of these operations that you see here are shorthand for various functions that are being defined. This is all predefined. It's all defined in the code base somewhere by the Python engineers. So this is how a typical class object works. You have basically a bunch of values, and you have basically a bunch of functions. You call these functions on some values to perform some operations. So as simple as that. So if you want to perform square root, you can do a square root operation with some libraries. So we'll come to what that is later on. So because before that, we need to learn what is called inheritance. So inheritance is something like this. You can think of it very simply. You have animals, and you have something like cats, let's say. Cats are also animals, but all animals are not cats, right? So if you have a class named animals and you have a class named cats, the class cat inherits some properties of the animals. Similarly, you could have a class named celestial objects. So every celestial object that we have in the sky will have some RA index. So I presume that you have already been taught what RA index are. RA index are right ascension and declination, which sort of denote the position of the object in the sky. So you have the RA index in the plane of the sky, and you have the distance to the object, the radial distance to the object. So these are available for any object. So if it's an extended object, you have a bunch of numbers. If it's a point source, you have like a single number. So you have these three numbers for any object. But then not all of these objects are stars. Not all of these objects are galaxies. Right? So you can say that every star has an RA Decan distance. But not every object which has an RA Decan distance is a star. So in that sense, if you have an object named celestial, so if you have every so if you have a class named celestial here, which contains RA Decan distance, and then you have a class named star. This star can inherit properties of the celestial and build upon those properties. So for instance, if you just look at the class celestial, the celestial contains itself, and it takes in three inputs: RA, deck, and distance. And it says my RA is so much, my deck is so much, my distance is so much. That's all celestial says. If you take a star, what it also takes is star type. So it says, okay, I'm a star, so I have RA deck and distance. So super of star itself, all it says is I'm giving these arguments to the celestial part of me. So it gives these inputs to its own RA Decan distance. And then it says, I'm not just a celestial, I'm also a star. So I also have a star type. So for example, Sun is a G2 type E star, and some other stars are different types. You have from O to M type stars. You can have whatever type you want. So that is another extra type, is an extra attribute of the star that is present. And I have defined a new function here called info. This info just summarizes what the various aspects of this star object. So it just prints. It says, no, I'm a star of type so much. My position is so much. My distance from us is so much. And just have a look at the way I have printed the statement. So I need to print some text here, and I need to print some values which are presented in the variable here. So the way I do it is I say f, and then double quotes, and then add the string here, and then have these two curly braces and put the variable name here. So this kind of notation is present in Python 3, and this is called f string. So if you want to print anything, let's say, so what was the x value here? I totally forgot. X is 2. Great. So I say print x value is, put the braces and say x value is 2. So this is how you can combine text with some variable names. So you can do this for debugging. You can do this because you want to say something to the person who is using it, because they want to understand what your code is doing. Or you can also use it if you want to put titles in your plots and all. And we'll come to this. So if you just define a class called celestial, and if you define a class called star, which inherits from celestial, we just defined it now. And then I say there's a star named Sirius. So I told you that there are animals, and then there are cats which are animals. And then if you have been to IUCAA, you can see that IUCAA is related with cats, right? And we have names for most of the cats present here. So we can every each of these names is a cat, but every cat doesn't have the same name. So the same way, you have celestials, of which you have some of them are stars, of which you have one star named Sirius. And this Sirius has specific properties. It has a specific RA index in the sky, and it has a specific distance as measured today from the sun, and it has a specific type. So if I say Sirius is a star with such properties, and if I say Sirius.info, this is what we get. Sirius is a star of some type and some distance and some position in the sky. So these values, these RA, deck, distance, star type, these are called the variable. These are the variables of the class, and these functions are called attributes. So these functions. So right now I just have an info function which just prints something out. But I can do functions to manipulate this. Let us say I am writing a code to evolve the star, and for some reason, let's say I also have the mass of the star as another input. As the star evolves, it starts to lose its mass because of winds, for example, let's say. So over time, I need to keep running this function, which in which the star is losing its mass because of the wind. It has to keep accounting for that. So every time I call the function, the star loses some of its mass. So I can keep modifying my class variables using these functions which are defined for itself. So this is the way the classes are being used, or classes can be used in for whatever purposes here. So numerical compute operations. So now we have some very basic understanding of what these classes are, how you manipulate them, how inheritance systems, so on and so forth. Oh, by the way, if you have some questions, just feel free to just stop and ask me questions. So, okay, I see there's some questions here. How to append in a dictionary? How to add key and item in an intermediate position? Okay. Append in a dictionary, I just showed you the luminosity example, I think. There is that. Yeah, I just showed you here. How to add key and item at an intermediate position? That's a very good question. It's not very trivial to add at some intermediate position because this dictionary is generally unordered. But there is something called an ordered dict, and we can use ordered dictionary to do that. Uh, maybe we can I can give you some reference material later on. Yeah. So with that, okay, let's come back to the scientific workflow. So we need to perform various numerical compute operations. What we have been doing right now is defining some variables and doing some very toy examples. But in scientific workflow, you're not typically working with toy examples. You have multi-dimensional arrays, and you need to do stuff with them. So generally, in Python, we use various packages. So good people all across the world. So this is how I call them. Good people all across the world. They have written a lot of packages for us. They have written a lot of codes, and then they said, look, we have written all of this code, and this code is very general. So why don't we make this public for people at large to use? And we can put caveats here and there on things that work, things that don't work, and so on and so forth. So for this, because of this initiative by some very good people, we have a bunch of packages which we generally use, and these are from the bread and butter for what we do. Without these packages, I don't think any of my work would be done. So what we do is we have these packages. We just install these packages, and what we do is we import these packages and just call functions from these packages. So the way we have defined classes here, these people have defined classes somewhere else. We just sort of copy paste their classes here and then use them. And copy pasting is not a very good way of doing things. So we just import them, which is basically we just link to whatever stuff that they have written and keep calling their functions and so on and so forth. So a bunch of packages that we'll be using is so first for array manipulation. So if you have multi-dimensional arrays, and you want to do whatever you want to do with them, let's say you want to do a matrix multiplication, you can use NumPy. NumPy is numerical Python, and this is something that almost everybody who uses Python uses. And then we just don't need to manipulate stuff. We also need to plot them. We need to see what the results look like, what data looks like. I'll show you what some data looks like. And for that, we need what is called Matplotlib. So Matplotlib is a very good plotting library, and any array that you give. So for example, any NumPy array that we have can be easily plotted using Matplotlib. Now, astro data is generally not in a very specific format called fits. So fits data has a specific format, needs a way to manipulate and load. And AstroPy is the go-to package for manipulating the fits data. So we'll be using AstroPy also. And finally, if you have tabular data, so for example, you're using SDSS. SDSS gives you, tabular data for whatever query you write. You can open or you can manipulate tabular data using what is called pandas. So you have these nice packages written, and all of them at some level support each other, right? So AstroPy is built on NumPy and Matplotlib and pandas to some level. Pandas has some is kind of built on NumPy and has a lot of support for Matplotlib, so on and so forth. So these four packages are what we'll be using today. And tomorrow, in the machine learning thing, we'll be looking at scikit-learn, which is a machine learning package. And if time permits, we'll also look at PyTorch, which is a deep learning package. Yeah, so let's not go into the tomorrow's thing. Let's look at tomorrow and not today. So what we do first is we import NumPy as NP. So I told you we need to install these packages, right? So the good thing about Google Collab, so the CO corresponds to collaboratory. So Google Collab is very nice in the sense that it has already installed all these packages for you and gives you for free. So you can ask how Google is earning stuff from this. Should ask Google how they earn stuff from this. But what it basically does to you is it has installed all these packages. You just need to import these packages and do whatever manipulation you want to. So you can say import NumPy as NP. So you're writing a shorthand for NumPy and saying in the NumPy folder, I call the NumPy folder as NP, and I import that, and anything present in the NumPy folder I'll be using henceforth as np dot something. And similarly, I say from Matplotlib import pyplot as PLT. So Matplotlib, so think of it like this. So Matplotlib is a GitHub profile, Git repo of Matplotlib. So Matplotlib is like a folder. It has multiple, so it has multiple files in Matplotlib, of which pyplot.py is one file. So this pyplot.py is what is being imported as PLT. The same way, so NumPy is actually a folder, but it also has an numpy.py file, and that has a list of all the functions. So we're basically just importing one Python file in our work. So just do this, just do a shift enter, and it has been imported. So all we are saying is we have a bunch of folders in which you have a bunch of files, of which we are just importing one file. So okay, we have some questions. Reference book for Python code learning. Okay, I have some references here given here. So if you go to the GitHub repo, then you can find a lot of references. So just click on this thing. So you have a lot of references given here. Just click on whatever links you want. And so, okay, there is a very technical question now. Seaborn and Matplotlib both are used for plotting and visualization. What is the difference between these two? Okay, so Seaborn is a okay, let's put it this way. Matplotlib doesn't have really good documentation and is not optimized for tabular data. Seaborn, on the other hand, is perfectly optimized for tabular data and has a lot of inbuilt plotting kinds. For example, if you have n variables and you want to plot the covariance between these n variables, it's just like one line in Seaborn. Whereas in Matplotlib, you possibly will have to write like multiple lines of code. So Seaborn is something that's it's built on Matplotlib to make it more beautiful, with better color schemes, with better support, and better support as in a very much better documentation and a better support for tabular data. Okay, so with that, let's get back. So now what we do is with NumPy we can actually define arrays. So what I say here is, again I take the same variable x. I keep manipulating it, right? Take the same variable x and say np.linspace minus 50, 50, 1000. What this, or yes, 1000. So what this means is I am going to take 1000 numbers between minus 50 and 50. So if I just do that, this is what you get. So it starts from minus 50 here and then goes all the way to 50. And the class here is called numpy.ndArray. So NumPy arrays are like the bread and butter for all the manipulation, or by and large the most manipulation we do here in science using Python. So what I can do with this, so see here, like what I can do here is I can define a Gaussian as np.exp. So I'm just exponentiating it. So every function is defined in a NumPy format, and what I do is x squared by 100. That's all. So x squared basically takes the square of each value present in x and then divides that by 100, and then takes the negative of that number and then exponentiates each value. So you can just say print Gauss. You get some bunch of numbers, And what you can do is you can say Gauss dot shape and x dot shape. Dot shape will tell you what the size of your array is. So you can say Gauss, the shape of this function of this variable Gauss is 1000, x is also 1000 because we selected 1000 points on the axis. And if you plot this, we get something like this, right? So it goes to 0. I mean, at 0, it is equal to f of x is equal to 1, and then it goes to 0 elsewhere. Very nicely. So this is how you take the typical NumPy array and then plot. So see how I plotted. So I say plt.plot of the x value, the y value, and I say the color of the plot, the color of the line plot is I want it to be red, and then I want the line style to be dashed, double dashed. And then I can say the x label is supposed to be x value, and the y label is supposed to be f of x. And then plt.title, which basically gives a title, is a Gaussian function. It's extremely intuitive for you to use because you know it's called x label, you know this is called y label, and you know it's called title. And all you do is just say plt dot whatever the function that you're calling. It's as simple as that. So this is your typical 1D plotting that you do in Python. Now what we can do is we can do something much more complicated, right? Let's look at let's define a 2D Gaussian of this form. So it's x minus 5 whole square plus y minus minus 5 minus 5 whole square plus something. So I just want to have a 2D, two Gaussians in 2D. So for this we need x and y, and we need to define this whole function. So this is x here. I'm just taking a small range for 1000 points. Again, I'm taking y here. I'm taking a small range. But then x is just in 1D. X is just a 1D vector, and y is a 1D vector. If you're seeing my video, what we need is a bunch of points all over the grid. So we need to have the square lattice of x comma y. So if you want to get the square lattice, what you do is you say np.meshGrid, and meshGrid will just will take the x and keep stacking x all over the space where the y is present, and it will take the y and stack it over for all the place where the x is present. And so you have x comma y at each point on the grid, and then you say double Gauss is whatever this function that I've defined here. That's it. And then I don't need to plot this here. I can do a plt.imshow. So imshow will plot the function, and then this is some random. So it goes from 0 to 1000, right? So because that's the range I have here. So it goes from 0 to 1000. I have two Gaussians here. And this scene map is the color map that you can give, and you can give a range of color maps. You can look at the Matplotlib documentation later on. But then we know that the x and y range from minus 10 to 10, right? It's not from 0 to 1000. 0 to 1000 is just the number of points. So what we do is we do a contour plot between x, y, and double Gauss, and say we have 100 levels, and see what happens. So if you do this contour plot, this is what we get. From minus 10 to 10, minus 10 to 10, we have these two Gaussians here, and which centers at these 2 points. And this is exactly what we have defined. So it's like at 5, 5, minus 5, minus 5, minus 10, 5, 5. This is the kind of Gaussian that we have defined. So this is how you can plot in 1D, you can plot in 2D, and so on and so forth. Now, there is something very special and important that you need to understand while you are working with any number or any array. There is something called not a number. So let us say you are taking some measurement on some instrument, and at some point you don't have data, simply because the instrument is not measuring, or there's some problem with the instrument, or whatever reason. So, but when you are generating the data for us, you can't simply say, oh, I didn't have data, right? So you would say that I'm giving you the full, I'm giving you a time series of whatever data I have, but then the data is missing for this range. So you should not use this range of data. So what people do is people generally associate missing numbers with something called not a number or not data. So this is called NaN, or not a number. It's a very special floating point value. It is meant to represent that this value is not a number. It is you do whatever you want with it, but it's not supposed to be used as a number. So it's a floating point value. So it's a float. It's not an integer. It's not a string. It's a float. And it's a float of nan, and whatever way you want to write nan as. And you can even say np.nan. All of them are basically nan. Nan. It's not a number. You can take, so nan is not equal to 0, it's not equal to 100, it's not less than 0. Nan is not, so if you can also say something. You can also ask this. If we say n5, that is n2.nan, n5 equal to n5, what is the result that you expect? So if I run this, what is the result that you expect? So let me know in the chat if you have run this, if you run this code, and then let me know what result you get here, and let me know why you would get this result. It will be an interesting exercise. So nan is basically not a number. It is used to represent in general very missing numbers or corrupted values, for example. Okay, so we'll see why this is important because we'll get some nans later on the data. So next, let's go and visualize some astro data. Oh, by the way, if you're running the Jupyter notebook, just run this cell and let me know what the results are. So, or if you can send, I don't know if you can send the message to everybody, but if you can send the message to everybody in the meeting, it will be a very nice discussion. Okay, fine. Anyway, so now we need to visualize some astro data, and I have two examples for you. So first example is basically a solar data because I am a solar physicist guy. So what we have is data is a solar loop, active region loop, and generally it comes in fixed format. So fixed format has two parts to it. There is a data part and there is a header part. The header contains information about the satellite, the location of the object, the resolution, the time cadence, and so on and so forth. It's all bookkeeping information that you need to understand how you got your data, what all manipulation was done to your data, and how science ready your data is. So that contains the header information. The data part of the fixed data contains the actual measured values of whatever the thing is. And what we'll do is we'll use a fits reader of AstroPy. So from astropy.io import fits. What this means is in the astropy folder there's a Python file named io.py, from which there's a folder named io. Sorry, and then in this you have something called a fits.py, and we are just importing this file. So you import this file and you just run this cell. So I'm just downloading some data here. I'm extracting some data here. I've done this already because it takes a lot of time to download. It takes 3 minutes, but it's a waste of time. And the way we open fits file is we just say fits.open, as simple as that. So we just say fits.open, and it says there is a primary HDU, there is an image HDU, there is a table HDU. So this image HDU is generally where, so actually the data here is present in the primary HDU. So it's not in the image or table HDU. So if I take the first primary one and say header, you get a lot of stuff like this. This is very, very, very verbose. So you say bit pick so much, number of axes is so much, the date is something, and then blah, blah, blah. You have a lot of information. So for somebody who is not interested in this or is not working in this is all junk. But for someone who is actually doing solar physics, this data is at some level very important because you need to know what your time cadence is, how much time the telescope was kept on for integration, so on and so forth. So this PC1, for example, PC11, PC12, for example, is the coordinate system, and you want to transform from one coordinate to the other, and so on and so forth. So C delta 1 is again the spacing in X and Y. So you have an image coordinate system, you have the real coordinate system in arc seconds. So you can see here that your units are in arc seconds in seconds, right? So what we'll do is we'll just take the data and header separately, and we'll see what the shape of the data is. So the shape is something, some 2987 and 420, 470. So what we'll do now is we'll just plot this image, and for this we'll use something called world coordinate system. So world coordinate system is a package, is a library in AstroPy, which takes in the header information of whatever fits file you have and generates a coordinate system which can be fed to Matplotlib to plot it. So all you need to say is WCS is something, some WCS of the header, and if you plot this, all this is what you get. See, so HPLN is helioprojective longitude, helioprojective latitude, and time. So last axis is time, or the axis which corresponds to 2987 is actually time. So the remaining two axes is just the coordinate, is the X and Y axis. So what we'll do is we'll plot this image. We'll say at the 58th time index, we just throw away this time axis because we don't care about it. We just want to plot an image. We say drop axis of -1, so last axis is gone, and we just plot the data. And look, the data was 2987 comma something, and here is something comma 2987. So the whole thing is flipped up. So WCS for some reason flips up the way the axes are represented. So you need to do it correctly, and just take just take that corresponding index, and let's see. This is what you get. So on x axis you have something in arc seconds, on y axis you have something in arc seconds, and this is a typical loop structure that's present in an active region. This is actually a flare of which I took some random index as one frame. Now what we can do is we can take two images and we can plot them one upon the other. So this is one image here. This is from a wavelength called 171. This is sensitive to the iron 10 ion, and this is 1700. This is sensitive to very low temperature emission. And if you just plot these two together, this is what we get. So you get one image overlaid on the other. So wherever it is red in color, it corresponds to the second one, which is the 1700. And wherever it is blue in color, it corresponds to the 171 image. So you can see that we have like a multicolored kind of image, and this tells you where very different kinds of emission are coming from. And what we can do is we can manipulate three images at the same time and just plot them as an RGB channel. So I have these three RGB channels here, and you see that each channel corresponds to a particular kind of emission. And if something is white in color, it means emission is coming from all the channels. If this is blue in color here, this beautiful thing is in blue color, and this blue color corresponds to 131, which is very, very hot plasma. So this blue is very hot plasma, this red is pretty cool plasma, and green is somewhere in middle, somewhere between hot and cool. It's very warm plasma. So this is the kind of plasma structure that this region of the sun has, if we can plot it all together at the same time. So this is what we get. Now I have an exercise for you. Okay, so we have some questions in chat, I guess. Okay, so how do you download the AI data? Okay. Okay, the IMShow part is basically just plt.imshow. It's nothing more than that. So you just run this cell. That's it. I have written this cell for you. So there's something called duplicate. If you use bash, it's just duplicate and a URL which I have generated. Just download it. That's it. It's nothing more than that. Just run this cell. As simple as that. So an image plotting is just plt.imshow. Very simple. So this IMShow takes in some x comma y as an image, and you can give a color mark, or you can give x comma y comma some 3-channel image, and you can get a color image like this, some RGB image like this. You can do that also. So this is typical image plotting and manipulation. Now I have an exercise for you. So you go home and do a Fourier transform of these images and see what different aspects of the Fourier transform give you. If you do a low pass filter, what do you get? If you do a high pass filter, what you get? So let's look at these two aspects of the Fourier transform. And if you have any questions, then I can join in early tomorrow and you can ask me these questions. I'll have a lot of time. So this is an assignment for you. I mean, you don't need to, it's not graded or something, but it's fun to do this when you do the manipulation. So just go ahead and just do it. And so let's come to the data frames part. So this solar data that we have seen is in fixed format. It's a bunch of images, but it's not always the case. You also have some tablet data, as I told you. So this data that we have here is from SDSS, and I have downloaded this data. It's available for free. So I have uploaded to a Google Drive. You can just run this cell and you can get the data out. So what we do here is we just import pandas as PD, and there is a CSV file. So I say pd.read_csv for reading this data frame. Will take some time to read. Okay, this has some chart images. Okay, how to make the RGB channel? Okay, fine. So I'll just show the RGB channel part again, and then we come back to the pandas. So what you do is you take the first image, do some manipulation to it. This manipulation is basically because if you have an RGB image, your color should be between 0 and 255 in each channel. Okay, only then is the RGB space defined. So think of RGB as XYZ, wherein the bounds are from 0 to 255 and integral steps. It can't be a floating point number. So you have the first channel here as AIA1, the second channel here as AIA2, the third channel here as AIA3. And then what you do is you combine these three channels. So you take first channel, second channel, third channel, stack them together. And the way you stack them together is you do something called np.asarray. Array means as array. You take the first one, second one, third one, and you just combine them. But when you combine them, what happens is it becomes the size is 3, comma x, comma y. So you have to transpose that. You have to take the RGB channel to the last. And so we just do a transpose and take it 1 to 0 and then do an asterisk int. So what you basically need to have is an array of shape x, comma y, comma 3. So if you have an array like that and you give it to plt.imshow, it will turn an RGB image. As simple as that. So that's essentially what it is doing. It's not doing anything more fancy. Okay, some of you are asking for references. I'll tell you about references later on. AstroPy references. So okay, so let's look at this tutorial first, and then you can go and look at the GitHub repo where I have the presentation, and I can show you, and the references are put up there. So what you can do is you have the data frame loaded up as using p.read CSV, and I can just say data.head. Head tells me just some aspect of the data frame. So what this data frame contains is this contains the object ID. It has the RA index. Obviously, I mean every object has an RA index. It has the flux in UGRIZ. So U is in magnitudes. Okay, remember that. So it has a flux magnitude in UGRIZ, and it has some what is it, housekeeping information. It has a spectral object ID, which maybe you can use to get the spectra of the object. Then it has the class of the object. So the LDSS folks have already classified these various objects into whether it's a galaxy or a quasar or a star. So there are three classes of objects in this data frame. It is a galaxy, it is a quasar, and there is a star. And then there's also the redshift of the object present here. And then again some other bookkeeping data. Okay. So basically what this table contains, it contains information about some point sources which are possibly galaxies or quasars or stars, and then you have the magnitudes, the distance, the redshifts, the position in the sky, and various other housekeeping information. So that's what this data set contains. We use this data set tomorrow for this ML thing that we do. So if you want to look at the values in RA, let's say, so what we do is we say data of RA dot values. So if you just do that, you get a bunch of numbers here. So to access the values in a given column, this is how you do. The data frame, and in quotes, single quotes, you see the column name and then dot values. If you want to know how many columns are there in this data set, you just say values dot shape. It's so many zeros after 5. Let me just count how many zeros. So it's a 5 lakh. So it's like 500,000 columns, rows are there in this data set. So 500,000 objects are there in this data set, which you can very easily do ML. Okay. And this is the number of columns, right? This is the number of rows, right? So if you want to look at the columns in this data set, we have already seen that in the previous line. So you have from object ID to RA deck to whatever, fiber ID and JD and so on. MJD is Julian date. So what we can do, so the way pandas and Matplotlib work together is that you can just say data.hist. Hist means histogram. Okay. You can say data.hist, and you can say which all columns you want the histogram for. So I don't care about the other column, right? So what I need to know is initially at least is the range of magnitudes that cover my data set. So UGRIZ is the range of magnitudes that I have. And so what I do is I can give a figure size, which the Matplotlib takes. I can give the number of pins, which again Matplotlib takes, and just say data.hist. So pandas calls Matplotlib internally and will generate this plot for us. That's why you are getting all this sort of crap here, all this sort of stuff that's coming up. So you can see U, G, R, I, and Z. You see distribution of the magnitudes that you will see everywhere. U, G, and R look nice, but if you look at I and Z, there is this minus nine 10,000 or something that's coming in the magnitudes. Obviously, you can't have the lowest magnitude you have in the sun is minus 26 if I'm not wrong. But then minus 10,000 is obviously it's not possible. Physically, it's impossible to have an astrophysical object or to have such large as in magnitudes. So what is this negative magnitude? Let's have a look at it. So what we can do is we can just take this ith column. So data of I dot min. Min gives the minimum of that column, and that minimum is actually some 9,999. It's a very small number. Let's see. Let's look at the chart. Okay. So it's a very small number. So this small number is a very specific number. Okay, it's minus 9999.0. So depending on the data type you have, the number of nines can change. But then it's a very specific number. So this specific number is a very old way of representing missing data. So nowadays people go with NaN, but earlier people used to represent this with, or rather it's like a legacy kind of thing that people still represent it missing data. So what we do, so what happens is basically a lot of these rows have the I and Z magnitudes missing for whatever reasons. So the value is missing there. What we can do is we can either interpolate across this data, or we can just drop these values, drop this whole row out. So I don't like interpolation, and we will not do interpolation here. And that is something for you to think about. Why we will not interpolate across data here? So what we'll do is we'll just replace this value with a NaN and then drop the NaN values. So if you just drop the NaN values here, it's all gone. And now if you do the same operation, data of I dot min, you can see that the minimum value now is some 7.6. So obviously this is not as bad as minus 10,000 or something. Right? So if you now plot the histogram of the values that you have, there you go. So in I and Z, it now looks reasonable. Between 10 and 25 is what the magnitudes you have. And this is kind of reasonable, makes sense. Physically it makes sense for us to have such magnitudes. So you see that even if I give you some well-made data, that data can have problems. Or it's not problems actually, because they're telling you what the problem is. You need to use them properly. So you need to first study your data, remove all the missing data, and pre-process it in some way. And only then should you start manipulating and do whatever you want with it. Because sometimes if we have a lot of data, we just get lost. We just don't carefully look at various aspects of the data, and this is very important. So in the solar case, we didn't quite look at the header information, but we just looked at the visualization of what the data looks like. But even there, you could have, for example, negative pixel intensities, and these negative pixel intensities come because of some random bias subtraction and so on and so forth. And these need to be removed, filtered out before you even do any manipulation. So you can see that this negative data, this missing data, rather not negative, this missing data is a very big problem. And you can mitigate it very easily by using replacing it with RANs and just dropping those particular rows down. So that is how we manipulate the tabular data. Now I have an exercise for you, another exercise for you. So the first exercise was first to do the Fourier transform. The second is I've shown you in this in another cells above how to make a 3-channel image. Now I would like you to use a library. This library is called Celluloid, and you can just take a snapshot over time and make a GIF for a video of the flare occurring in any 3 passbands that you like. So this will look very beautiful if you sort of spend some time and get it working. So if you find time, then just do this and send me an email or something. It'll be very nice. So that's it I have for today. And if you have any questions, just feel free to ask me. Okay, so I'll stop sharing my screen, and maybe you can just raise your hands or something, and I can ask, and I can unmute you. You can ask your questions. Meanwhile, I'll read the chat and see what the questions you have. Yeah, Mahinder, please go ahead.
Sir, nice talk, sir. Sir, as you said, you are the solar physicist. Sir, how can we measure the size of the sunspot by using SDO images by using sunspots? Can we?
Yeah, you can do that actually because nowadays the data is already fixed, right? So what you can do is you can sort of crop the area around the sunspot, and you know the coordinates because fix gives you the coordinates itself. And if let's say you put a circle around the sunspot, assume a circular sunspot generally, and so you know the extent in arc seconds, and then you can figure out what the size of the sunspot is. It needs some manipulation in the sense that first figure out a circle around the sunspot, and then get the exact coordinates of the extent of the sunspot. But it's quite doable. If you use SunPy, for example, I didn't teach you SunPy, but if you go and study SunPy, it should be it should be very easy to do.
Yes, sir. Next question is that only. How do we use SunPy modules?
Okay, so SunPy has something called a map object. So a map object basically has a data part. It separates the whole thing out as a data part and as a coordinate part. So if you do a cropping in the data, you can also crop in the coordinates, or you can crop in the coordinates. You can crop in the data. You can do all of that manipulation. So with that, you can see you can go in the pixel coordinates. What pixel coordinate your sunspots leftmost extreme is, for example, and you can translate that to what real world arc seconds it is, and you can do the same thing for the other extent, and then you can get a size estimate in arc seconds. Now that is in arc seconds. We want it in kilometers, let's say. Then this is a conversion. So for example, SDO, one pixel is 725 kilometers, I think.
How much? 17? How much?
725 kilometers, I think. Each
Yes,
pixel.
sir. Yes, sir. 17.
Each pixel. Yeah. So
that means 1 arc second, right?
that is not 1 arc second because one pixel of SDO is 0.6 arc seconds. So if your sunspot is in full resolution, if it's like a I don't know some n number of pixels, then it's 720 times n, and it's like 30-40 megameters is what sunspot sizes are. So a couple of hundred pixels, I guess. I don't know. Let us see.
So because I'm working on a solar radio burst, sir, actually.
Okay.
To analyze some solar signals.
I see. No, it should be. Once you can figure out in the pixel coordinate system what your sunspot size is, then it's just a transformation to whatever your actual size is, right? Because that is very well defined transformation. That should be trivial to do. You can read the transformation in the SDO, the SunPy documentation.
Thank you, sir.
Yeah. Yeah, more questions. More questions, clarifications.
Sir, particularly your specialization is what, sir?
I work in solar wind and Cornish heating. Yeah. Just call me Vishal, by the way. Not very old or anything. So it's fine. So okay, yeah. So I answered your question. So Sneha asks, she wants to learn astropy properly. What should I refer for the same? Oh, you should read astropy documentation. Astropy documentation is very well done, and so all of this documentation, astropy, numpy, Matplotlib is okay. It's getting there, but it's not excellent, I would say. But astropy, numpy, even sunpy documentations are very good. Just go and read the documentations. But it's not like a novel, right? You just don't go and start reading it. You need to have something to work on. So go there, look at the tutorials first, and try to do those tutorials by yourself, and that's how you learn. So and then you will obviously get stuck in something. You'll get stuck first of all in installing something. So you start from there. You grit your teeth and go ahead a bit, and then finally you will figure out. It gets easier after some time. So that's how you learn. Otherwise, there is no. You obviously have a lot of books for learning Python and things like that, but at some level, it doesn't really help. You need to get your hands dirty and actually work on something. Right? Only then it makes sense. Okay, so you're not able to understand how to get the AI data. Okay. The wget command. Okay, fine. So wget basically is a web getting command. Okay, let me just share the screen again. So it's basically just a web get command. What it basically does, okay, let's hear. What it basically does is wget and the URL here. Okay, this URL. So I just what I'll do is I'll just copy paste this URL here. If I can go to my next tab, so I'll just copy paste here. This thing will load and it will ask me to download the data. And you see, it's asking me to download this data as a tar.gz file. So this URL I have already generated for you by looking at some event. So I've done the hard work for you to get this particular event out. And all you need to do is just go to the website and get the data out. So getting data is just a simple wget command. So just wget this thing, and what it does is you can see this folder option here. And you click on this folder option in your Collab, and you can see that all of these files are downloaded here. The star.gz file is present here. And then when you do a tar, not tar, so when you have a not in front of your command, it means it's a bash shell command. It is not a Python command. So there are Python commands where you're doing import, export, and stuff like that. Then there are bash shell commands which are just slightly different, which are not Python commands. It's a different language. So we are using wget, which is a bash shell command, and we are using the tar, which is again a bash shell command. So what I'm doing is I'm just saying I have this file here, this some file here, and I want to extract the contents of this file in the same location. So I have this file, this tar.gz file, and I've extracted all of these files in the same location here. That's it. So once I do that, all the files are present here, and then I can just run astropy fix.open and load the files out. That's it. Does that work? I use Ubuntu, no problem. Okay, I'll use Ubuntu. Okay. Yeah, it should be easy for you to do. Can we get data from somewhere and detect sunspots for a practice? Yes, you can get data for sunspots. There is a sunspot. Okay. So can you just unmute and ask, do you want sunspot number as a time series or do you want images of sunspots? You can just unmute and ask, I think. You have the permission. Okay, fine. Images. Okay, images is going to be a bit difficult, but Kodaikanal Solar Observatory has a lot of image data of sunspots. So you can use that. So I think you can go to Kodaikanal's online repository where you can find all the data. And I think there are sunspot data, calcium 2 data. Okay, you can just go and find it out. That is there is something called SILSO, SILSO. That also has some data. I don't know if they have images or not, but they do have the time series. So check it out. Maybe it's there.
Sir, from the wget command, shall we download any text files of long series datasets?
You can download whatever you want with wget. I mean, if you have some, I don't know, if you have some movies or something somewhere, you can download that also. So I think if you can do it, you can do it. So wget simply gets the file that's present in a server somewhere. That's it. That's all it does. So
there are year-wise data is there, no? It's automatically downloaded.
No, so for wget you need a particular URL, a particular file URL, and which is what is used to download. So if you want to automate over a bunch of files, then you have to put that in a for loop or something, and then you can do it. So there is something called parallel wget, which downloads multiple files in parallel. So you can do that. So just check the documentation of parallel wget. You can get a bunch of different files for different years, let's say, and then you can just download this. So for the file that I've used, it basically is one tar file which contains multiple files. So it is easy, just like one command. So any more questions, queries, clarifications? Well, I think everybody is tired. Everybody wants to have lunch now. So yeah, so you this notebook, I'll just share it again for people who might have joined late. Some people have left also, but anyway, it's fine. Everybody in the meeting. So I'm sending this link again, and this link contains the repository where all the codes for today and tomorrow are present. All the presentation files are also present. So, so the edits I've done today, just to show you some stuff that's not present. So it's all very clean for you. So you can just go there and do your home assignments and play with the data. So this data is public, right? You can play with it and do whatever you want. Just go wild with it. Okay. And if you have some queries, then just get back to me, or you can join a bit early tomorrow, and I can clarify your questions if you have some. Okay.
Thanks, Vishal. I
Yeah.
added the GitHub link on the Slack channel.
Yeah. Thanks, everything. Yeah. So shall we close now? Is that fine?
Yeah, sure. We can. Yeah.
Okay.
Thank you. Thank you.
Okay. Yeah. See you, Bye.